Hello students, in today's lecture we will discuss the numericals on the topic interference, more generalization, reflection in thin films due to reflected and transmitted light, and a few questions on the spread of your light beam. Let us begin. First, let us quickly revise the formulas. Coherence length, which means that for this much amount of time our light is traveling in a very coherent manner. Distance is speed into time. With this formula, coherence length becomes equal to c into tau c, where c is the velocity of light for electromagnetic wave or other waves, wherever the velocity is given, and tau c is your coherence time or the temporal coherence. We have two types of coherence, temporal coherence and spatial coherence. Second formula, frequency spread of the spectral line. Frequency is proportional to time. So frequency spread is approximately proportional to 1 upon tau c, where tau c is again your coherent time. Spectral purity, that means how much pure is my spectra coming, is equal to, we see spectra only in interference pattern etc., is equal to lambda upon del lambda, and we know the formula that velocity is equal to frequency into lambda. So from that formula, lambda upon del lambda becomes equal to del mu upon mu, where mu is frequency. Coherence length can also be written in terms of purity factor as coherence length is equal to lambda square upon del lambda into equal to q into lambda. Spatial coherence length, that means the amount of spread in space, is equal to lambda upon theta, where your lambda is the wavelength and theta is the angle subtended by the slit. For circular aperture, the spatial coherence length is equal to 1.22 lambda upon theta. Let us begin with the numericals. In Michelson interferometer experiment with helium neon laser, fringes are visible up to a path difference spread of 8 meter. You have to find the lower limit of coherence length, coherence time, spectral line width, and purity factor. You have been given the wavelength equal to 11.5 into 10 to the power of minus 7 meter. One more thing, 1 angstrom is equal to 10 to the power of minus 10 meter. So the path difference spread is equal to coherence length 8 meter. Coherence time is equal to, we know distance is equal to speed into time. So coherence time is this length upon speed. Speed will be taken as velocity of light, 3 into 10 to the power of 8 meter per second. Spectral line width, that means del mu is equal to 1 upon tau c. Tau, that is the coherent time you have found, you just have to take its inverse. Purity factor is equal to ratio of mu upon del mu, which is also equal to c upon lambda into del mu. We put these values from above expression and we get our answer. Next question. Michelson interferometer is illuminated by a source of light whose wavelength has been given to us as 5890 angstrom. This interferometer is set for zero optical path difference. Now, through what displacement the mirror of interferometer should be moved so that interference fringes are going to disappear? Now see, if the optical path difference is larger than coherent length, then your interference fringes are going to disappear. So in Michelson interferometer, optical path difference is twice the distance that is moved by the movable mirror. So coherence length is equal to 2d, which is equal to lambda square upon del lambda, where lambda is wavelength. So d is equal to lambda square upon 2 del lambda. All these values have been given to us in the numerical. We just simply put them. Angstrom has been converted to centimeter. 1 angstrom is 10 to the power of minus 10 meter or 10 to the power of minus 8 centimeter, and we get our answer. Next question. The frequency frequency range of neon spectral line has been given to us is 10 to the power of 10 hertz. You have to find the coherence time and coherence length. Coherence time is equal to 1 upon del mu. Simply put this value of frequency which has been given to you and you get the answer. Coherence length is speed into time. So speed is 3 into 10 to the power of 8 and time is 10 to the power of minus 10. Determine coherence length and coherence time for white light. You have been given the frequency of violet light and the frequency of red light. So the frequency spread will be del mu is equal to mu of violet minus mu of red, and coherence time will be inverse of frequency. Coherence length will be speed into time. Simple relationships. The coherence length of helium neon laser is 15,000 kilometer, and the wavelength of light used is 632.8 nanometer. That becomes 10 to the power of minus 9 nano 9. Calculate the bandwidth and frequency spread. Let LC be the coherent length, lambda the wavelength. So the bandwidth del lambda is equal to lambda square upon LC. Now this nanometer we will convert to meter, and 1 meter is 100 centimeter. So we are going to convert this meter, and after that this wavelength we will change from kilometer to meter, because we have to do all units in a normal fashion for numericals. Otherwise our answer will come wrong. So 1 kilometer is 1000 meter. Now see, everything is in meter. Straight away put it in the numerical and you get the answer. So frequency spread is 1 upon tau c. That is your coherence time. So del mu is equal to C upon LC. Next, interference in thin films. First, revise the formulas, especially where does maxima come and where does minima come. First case, reflected light. Here, total path difference will be 2 mu t cos r minus lambda by 2 from Stokes' law. That can be plus minus lambda by 2 if you are applying Stokes' law. If you are not applying, then it is simply 2 mu t cos r. Now, constructive interference or maxima is equal to this 2 mu, the path difference is equal to 2n lambda upon 2, the even multiple, and when n is equal to 0, then path difference becomes equal to 2 mu t cos r is equal to 2n plus 1 lambda by 2. When n is equal to 1, then it is 2n minus 1 lambda by 2. For destructive interference or minima, it is 2 mu t cos r equal to n lambda, where n is 0, 1, 2, 3, etc. Interference due to transmitted light, we will not apply Stokes' law. If we see the medium, so it's simple path differences 2 mu t cos r. Constructive interference or maxima, it becomes 2 mu t even multiple, that is 2 mu t cos r equal to n lambda. And for destructive interference or minima, it is 2 mu t cos r is equal to 2n minus 1 lambda by 2, where n is 1, 2, 3, and 2n plus 1 lambda by 2, where n is 0, 1, 2, 3. Another thing, if the numerical says for thinnest film, then put n equal to 0. If the numerical says light is falling as a normal incidence, then put r angle of refraction equal to 0 for the numericals. Now, one more thing. Snell's law states that mu is equal to sine I upon sine r, and sine square theta plus cos square theta is equal to 1. And for a very thin film, you straight away put n equal to 1. Let us begin. A parallel beam of sodium light, all usually interference numericals carry sodium light only, whose wavelength range falls in this range of 5893, 5896 angstrom, etc. since because it is a assumed monochromatic source of light. So it is incident on a thin glass plate of refractive index 1.5 such that the angle of refraction has been given to you as 60 degree. Now you have to find the smallest thickness of the plate which will make it appear dark by reflection. So dark means I have to use the formula for destructive interference or the minima, that is 2 mu t cos r is equal to 2n lambda by 2. I have been given mu 1.5, r 60 degree, lambda 5880 angstrom. This angstrom, 1 angstrom is 10 to the power of minus 10 meter. I will convert it into centimeter. Cos 60 degree is half or 0.5. For smallest thickness, I will put n equal to 1 and I will get my answer. Next numerical, calculate the thickness of the thinnest film with mu equal to 1.4 in which interference of violet component of incident light can take place by reflection. That means you have been given colors. So obviously if colors are there, we will take the case of maxima, that is constructive interference in reflected light. This you have to decide after reading the question, whether it is a case of maxima, whether it is a case of minima. So constructive interference in reflected light system, 2 mu t cos r is equal to 2n plus 1 lambda by 2, where n is 0, 1, 2, etc. Again, for a thinnest film, n is equal to 0. For normal incidence, r is equal to 0 and cos 0 is 1. Lambda, I have converted into centimeter. Putting all these values in the above equation, I get my answer. A man whose eyes are 150, here is the human eye, 150 centimeter above an oil film on water surface, he observes greenish color at a distance of 100 centimeter from his feet. This is the person standing OB and this is his feet length distance. You have to find the probable thickness of the film. See, if T has been assumed as thickness and R is the angle of refraction, then we will be applying the condition of maxima in reflected light because we are seeing the color. So this becomes equal to 2 mu t cos R is equal to 2n minus 1 lambda by 2. And we will put the value of T, lambda angstrom we will convert to centimeter, refractive index of oil we have been given, 1 angstrom we will convert. Now look at this triangle OAB, tan I perpendicular upon base, 100 upon 150. Similarly, sine I. So you can find out the hypotenuse and then you get the value of sine I from Snell's law. Mu is equal to sine I upon sine R. So sine R becomes equal to sine I upon mu. And we get, and sine square theta plus cos square theta is equal to 1. So cos R is equal to 1 under root 1 minus sine square r. Putting these values in the formula, t equal to 2n minus 1 into lambda by 4 mu cos r, we get the answer. For other values of n also, you can similarly get the answer. When light falls normally on a film of soapy water whose thickness has been given and refractive index as 1.33, which wavelength in the visible region will be reflected strongly? When light falls normally, R becomes 0 and 2 mu t into 2n plus 1 lambda by 2 for n equal to 0, 1, 2. This formula we will use. T has been given to us. Putting these values, we get the answer for T. Now for different values of N, we can see the answer and we know that our visible range lies in the region of 4800 to 7800 angstrom or approximately 4 into 10 to the power of minus 5 centimeter to 7.5 into 10 to the power of minus 5 centimeter. So out of all these given wavelengths, only these two, the 7 one and this lies near the upper limit of the visible spectra. Hence, this is most strongly reflected. When light is incident normally on a thin film of thickness this much and index of refraction 1.5, find the wavelengths in the visible region reflected most strongly. For normal incidence, R is equal to 0 and we will use the condition of maxima, 2 mu t into 2n plus 1 lambda by 2. And we will put these values here, simple. T also we will change this for n equal to 0, n equal to 1, n equal to 2, n equal to 3, n equal to 4. Now we can see from these readings only this value and this value is lying in the visible region, 400 to 700 nanometer. Hence, these two wavelengths will be reflected most strongly. A soap film has been given of refractive index is illuminated by white light incident at an angle of 30 degree. The refracted light is examined by a spectroscope and you have to find out the thickness of the film. See, the condition for destructive interference here will be 2 mu t cos r is equal to 2n lambda by 2, even multiple. All values have been given. Use Snell's law. Mu is sin I by sin r, and you get the value of sin r. Sin square theta plus cos square theta is equal to 1. You get the value of cos r. Put these values and get the answer. A parallel beam of sodium light strikes a film of oil floating on water. When viewed at an angle of 30 degree from normal, eighth dark band is seen. So you will use the formula for dark. 2 mu t cos r is equal to even multiple. All values have been given to you. Snell's law, sin square theta plus cos square theta equal to 1. 1 angstrom equal to 10 to the power of minus 8 centimeter. Quickly put the values and you get your answer. Calculate the thickness of a soap bubble film whose refractive index has been given to you, which will result in constructive interference in the reflected light if the film is illuminated with light whose wavelength in free space is 6000 angstrom. So this is the condition for constructive interference in reflected light. So 2 mu t cos r equal to 2n minus 1 lambda by 2. And light is incident normally, so r equal to 0, cos 0 equal to 1, least thickness of the film, n equal to 1. Simple, you get the answer. Light of wavelength 5893 angstrom is reflected at nearly normal incidence from a soap film of refractive index 1.42. What is the least thickness of the film? That will appear dark and bright. Now, condition for dark is 2 mu t cos r equal to n lambda. For normal incidence, r is equal to 0, cos r is 1. So you get t. Least thickness of the film, n equal to 1, and you get the answer for t. 1 angstrom, 10 to the power of minus 8 centimeters. The condition for brightness of the film in reflected system is 2 mu t cos r equal to 2n minus 1 lambda by 2. Normal incidence, cos r, you put the value and you straight away get the answer. When light is incident on the soap film at an angle of sine inverse 4 by 5, reflected light is observed with the spectroscope. It is found to have two consecutive dark bands. Consecutive means 1 by 1. So, if n and n plus 1th are the orders of consecutive dark bands for wavelengths lambda 1 and lambda 2, then your formula is 2 mu t cos r equal to n lambda 1 and 2 mu t cos r equal to n plus 1 lambda 2 because it is consecutive. Just equate them, find an expression for n, put this value of n in your expression for t, and again same step, Snell's law, mu equal to sin I by sin r and cos square theta plus sin square theta equal to 1, and lambda, convert it into centimeter. Mu has already been given to you as 4 by 3. Putting these values, you get the answer. A film of refractive index mu is illuminated by white light, and now in reflected light, two consecutive bright fringes are observed. Obtain an expression for thickness of the film. Bright fringe in reflected light, 2 mu t cos r equal to 2n minus 1 lambda by 2 for n equal to 1, 2, 3. If it had been 0, it would have been a plus here. Now you are taking consecutive. So n and n plus 1 are the orders of the consecutive bright rings corresponding to wavelength lambda 1, lambda 2. You quickly put the values, equate these two equations because here you can see they both are same. Equating, you get an expression for n. Once you get the expression for n, use Snell's law. Cos square theta plus sin square theta equal to 1. Simplify, put the value in formula for t and you get the answer. White light is incident on two parallel glass plates which are separated by an air film of 0.001 centimeter thickness, and the reflected light is examined by the spectroscope. Find the number of dark bands seen in the spectrum between these wavelengths. See, condition for dark band in reflected light is 2 mu t cos r equal to n lambda. You have been given mu, t and I. Range of visible spectra approximate is 4 into 10 to the power of minus 5 to 7 into 10 to the power of minus 5 centimeter. So let number of dark bands seen be at lambda n1 is this much and n2 be this. Again, same procedure, Snell's law. Here, since the medium is same, so mu will be 1. When mu is 1, sin I is equal to sin r. So simple, you put it cos r is root 3 by 2 and lambda, putting these values in 2 mu t cos r equal to n lambda, we get this for wavelengths, both the wavelengths n1 43, n2 24. So number of dark bands observed within the given spectral range will be equal to n1 minus n2, which is equal to 43 minus 24 equal to 19. Thank you.